This video is about special products of polynomials. We're in the context of a beginning or introductory algebra course, and we've already discussed some exponent rules, so we'll be relying on those that we already know. And we've also multiplied some basic types of polynomials together. Now these rules will give us some shortcut formulas for certain cases of multiplying polynomials. And let's start with the case known as the perfect square. This type is when you start with, let's say, a binomial of a plus b all squared. So a plus b is in parentheses and then you're squaring it. Or it's the same thing if you have a minus b in parentheses squared as well. So plus or minus works. But they each have a special formula. Now, there's not actually that much special about these. These are really just the results of using the FOIL process to multiply these original forms together. So if I had a plus b squared, a plus b in parentheses all squared, that could be written out as a plus b times a plus b in parentheses each, and then foiling them together would result in the other side of this shortcut. So it's a squared plus 2ab plus b squared. Again, that is really nothing more than foiling the a plus b times a plus b, combining like terms, and that's your result. But if we treat this as a special shortcut formula or special product, we may be more likely to memorize it and then be able to use it quicker. The other one, a minus b all squared, turns out to be a squared minus 2ab plus b squared. Again, same thing, you just FOIL out a minus b times a minus b, and that's the result after combining like terms. Notice there's only one real difference between these, and it's, I think, useful to point it out. So the first sign in the result, the special result, actually matches the sign that's in between the original terms in parentheses. So when we had a plus b in parentheses squared, then the first sign of the result was a plus sign. It's a squared plus 2ab plus b squared. So that's true for both of them. If you look at the minus sign between the terms in the second case, a minus b all squared, you end up with a squared minus 2ab plus b squared. Let's try some examples now where we use a perfect square formula, as described above, to simplify the following. Our first example is a set of parentheses containing x plus 5, and then those parentheses are raised to the power of 2. So you could call this x plus 5 all squared. Now, this could be done, as mentioned, by writing out two of these, x plus 5 times x plus 5, and then foiling those together. But we're going to try to practice using these special forms that we've already listed above. So to do so, let's first of all identify the pieces. So the first part, in this case the x, the first term, that's going to be like the a that we have listed above in these formulas. So it's good to just kind of note the pieces here. That's the a, and then if you look at the second term being 5, that'll be like the b value in the formula we've used above. Now, noticeably here, I didn't talk about the sign between the x and the 5. Typically, we say that a sign in front of a number goes with it. So you'd say like that's a positive 5. But actually, the sign in between these terms is going to just simply determine which of the two formulas we use, because that's the difference between them. So we'll note that this is the positive or the plus version, and it's good to just recognize that, and that should show up when we get to the formula. Now, if a is x and b is 5, let's understand the general structure of this formula. This would turn out to be a squared. I'm going to call that blank squared for a second. The first sign is plus because that has to match the sign that's in between our terms. So we have blank squared plus, and then it's 2 blank blank plus blank squared. Now there's a lot of blanks there, but if you go back up to the formula, you can see why we need them. Let's furthermore coordinate those blanks with how they'll line up. So we said already our first term x is like the a. In this formula for the plus version of it, we have a squared plus 2 AB plus B squared. So the A occurs in those first two blanks, and then the B occurs in the second two blanks. It can be useful just to kind of see this separated that way to know exactly how to put in all the different pieces. So anywhere I see a blank where the A should go, I'm going to put the value of X, which we've already assigned as the A value. Anywhere I see a blank where the B should go, I'm going to put the value of 5, just like we said above. And I have the plus sign first, aligned with the plus sign for our original problem, which means we can go ahead and just kind of finish by cleaning this up. Instead of x in parentheses, I can just call it x squared, keep the plus, and then 2 times x times 5 is really 10x, and then plus 25 instead of 5 squared, and that's the result. Now, this should be the same result you would get if you FOIL these out originally, x plus 5 times x plus 5. Sometimes you can do that to check. But this formula, when you memorize it, can be a lot quicker. Of course, if you don't know it or forget it, then it's not really that useful. So just be mindful of maybe the benefit of memorizing it. Let's try another example. The second one reads 5x plus 2, all in parentheses, squared. Well, if we go through the same process and identify this is another plus version, we have an a as the 5x and a b as the 2, then we could call this 5x in parentheses squared plus 2 times 5x times 2 plus 2 squared. That's just plugging the pieces from this problem in the right places in the formula. And now we'll simplify. 5x in parentheses squared is really 25x squared, just squaring both the 5 and the x, given the exponent rules we've discussed. Then we'll move on to say plus. Now 2 times 5x times 2 is really a 20x, and then plus a 4 with the last term, and that overall result is our simplified answer, 25x squared plus 20x plus 4. Let's try another example. This one begins with a set of parentheses containing 2y minus 1/2. And this set of parentheses is the same kind of setup. It's a difference, though, this time with a minus in between. So we'll identify the 2y as like the a part and the 1/2 as the b, and then use the formula as a squared, so that's 2y squared. We're going to use a minus this sign to match the sign between these original terms. And so minus 2 times a, which is 2y, times b, which is 1/2. And then it's always the plus or positive at the end here, so plus b squared, so that'd be a 1/2 squared. Now, for this case, we want to go through and clean this up, of course. 2y squared is 4y squared. If we multiply what's in the middle term here together, we have a 2 times 2 times 1/2. Well, that's really just 2. So we have minus 2y in the middle, and then we have a plus 1/4, which is that 1/2 squared. Let's try another example. This one begins in parentheses with x to the 8th plus 5, and then we square those parentheses. Well, like we've been doing, we just match it up with the setup of the formula above. So a is like the x to the 8th power here, and b is like the 5. So plugging this in, this is the positive version. So we have a squared, that's x to the 8th squared. Keep the sign the same for the first, so plus. And then it's 2 times a, so 2 times x to the 8th, times b, so times 5, plus b squared, so 5 squared there at the end. Then we'll go ahead and simplify using our exponent rules that we know. When you see x to the 8th in parentheses squared, those powers will end up being, do you remember it? Multiplied together. So this would be x to the 16th plus, now in the middle we have 2 times 5, which is 10, and then x to the 8th, and then at the end plus a 25 for our simplified results. There's one more special form we want to discuss in this topic or this video, and that is what's called a difference of two squares. So what we just did previously here was called the perfect square, as you recall. This new form is called a difference of two squares. Now, the way it works is you could start really on either side, but if you ended up with a plus b in parentheses times a minus b in parentheses, then of course you could FOIL those together like we've been doing, but the result, once you combine the like terms, would end up being a squared minus b squared. Hence the difference, there's a subtraction between these two squares. That's where it gets the name, difference of two squares. And this little setup, or this formula, special form, is very useful, especially when we get to factoring, which is when we're going to go backwards from right to left here. We're kind of just going from left to right at this point by multiplying these two binomials together. So let's go ahead and try using this form to speed up our process and multiply some of these together. The first example I want to try has two sets of parentheses. The first set contains 5z minus 2. The second set contains 5z plus 2. So you can recognize the different parts of this that match up with the formula above. So the first term, the 5z, matches in both sets of parentheses. That's like the A. And the second term differs in sign, so it's minus 2 and then a plus 2, but the 2 is kind of like the B. So if we understand those pieces and put them together with the formula above, we end up with a squared minus b squared, where the a is the 5z, as we've said, and the b is the 2. So if we simplify these algebraically, 5z in parentheses squared is really 25z squared minus, and then 2 squared is 4. So 25z squared minus 4 would be the result. Again, you could get this exact same result if you had simply FOILed these together and then combined like terms, but this is using the shortcut formula to do it. A next example involves two parentheses, and at the beginning they include 3y plus 1/3 and then 3y minus 1/3. Notice the plus and minus, these always have alternating signs, but the order of those doesn't matter. In the first example, the minus was first and then the plus. In the second example, the plus is first and the minus, but the order of those two signs doesn't matter, it doesn't change the formula. So let's go ahead and figure out that the first term in each set of parentheses, the 3y, that's like the a, so we want 3y squared, as in the a squared for the formula, and then we do minus, and then b squared, this time the b is the 1/3, and so we'll go ahead and simplify these. 3y squared is 9y squared, minus 1/3 squared is 1/9, and so 9y squared minus 1/9 should be our simplified result. Let's try a couple more. The next one has m cubed plus 4 times m cubed minus 4. Again, notice the pattern. The same thing in the beginning, that's like the a, and then just the different signs for the second term. So a plus b, a minus b. If we return this into the result of the formula we have above, the shortcut formula, it's a squared minus b squared, where a in this case is the m cubed and the b is the 4. So simplifying this, m cubed squared, we'd multiply those together to get m to the 6th minus, and then 4 squared is 16. So m to the 6th minus 16. Moving on to the next one, this one begins as two sets of parentheses. The first one contains 7x cubed plus 5. The next one, the second one, contains x squared plus 2. But if you try to start to match this up to the formula above, you'll notice it actually doesn't match. So I'm going to say here, this does not fit. Doesn't fit the formula above. This is not the a plus b times a minus b, for two reasons. The a, the first term, doesn't match. We have 7x cubed and x squared. And same thing, the last terms don't match either. We have a plus 5 and then a plus 2. So not only are they not different signs, they're just totally different numbers, which means this doesn't fit, which means you have to FOIL this one together. That's the only way to multiply these two together. We have to just rely on the FOILing, which again does work for the other types, but those match the formula, the special one. This would be just FOILing together. So first times first would be a 7x to the 5th. Outer times outer would be a plus 14x cubed. Inner times inner is a plus 5x squared. and last times last is a plus 10. You'll also notice that there are no like terms in this result, which means there's nothing to combine, which means we're done with this.